let's talk about where we're at now. So, lectures, the last few lectures talk about chapters 4 and 5. That's exam 2 material. Now there's the end of chapter 5, that if you're following along in the textbook, you'll notice there's a section 5.5 that we haven't talked about yet. That is unsteady flow. Unsteady flow, I'm not going to put on any exam. It won't show up on this exam. It's not going to show up. It's not going to be a topic we have to worry about for exam 3. It's not going to be a topic for the final exam, even though the final is comprehensive. We're going to talk about it. Okay. It ties together pieces of both chapters 4 and 5. We're just going to kind of mention it and tidy up. It's a kind of an optional topic I like to talk about when we talk about chapter 5 if we have time, and we are kind of right on schedule and really kind of a little bit early. I kind of try to build a day like today in where, especially in the summer, give you guys a chance to try to work through that homework, really focus on it, not try to rush through it too much. Anyway, some of you guys, anyway, just give you guys an opportunity to not only just work the homework, but additional problems like the homework, get some practice in. So this is kind of a topic that we can talk about, not on an exam, but I do think it's going to be helpful for you, okay? So, with that said, exam 2 is coming up. So I'm recording these videos to post on June 25th, is that right? Yeah, so no, yes. June 25th is when I'm planning to roll these videos out. So the Thursday after that will be July 2nd. And so that's right before the Independence Day holiday. We'll get exam 2 done out of the way. And so we'll talk about the exam on Tuesday, the end of June, so a few days from today. And so if you have questions, let me know. By the way, I don't have PowerPoint here today. For some reason, these slides did not want to show up, so I'm just showing the preview through Canvas. It seems to be working here, but it's not. My copy of PowerPoint on my tablet did not want to display the equations I have built in here. So, well, there's more than one way to do that, right? And I know I could do a screencast, but anyway, this seems to work. So here we are. We talk about unsteady flow. Again, the end of chapter 5 in the Changle and Bowles text. Unsteady flow refers to this warm-up period or this cool-down period where if you look at the conservation of energy and the conservation of mass, you have this change period where the change, which normally with the control volume we say, well, it's 0. We normally worry about the steady flow condition where the dm dt and the dE dt both go to 0. Everything's constant with respect to time. Here we're considering a situation where, before we reach that steady flow point, you've got to warm the system up. You've got to get everything spinning. You've got to fill it up, get it operating. Or after you shut everything off and everything's still kind of going and spinning and it's got to cool down. So there's a period of time where the system itself, the device, if you will, is either warming up or cooling down, or it's filling up with mass or it's losing mass. The example I always like to give is the garden hose, and I've used this metaphor before, but I think it's valid here. If I go outside on a warm, hot day, which is, we're recording these in the summer, so we can kind of experience that. If you go outside and hook up a garden hose that's been sitting out in the sun, hook it up to a water faucet, and you turn it on, and do you get water out of that faucet immediately? No, there's a period of time where the water hose, if the water hose is my system, there's a period of time where the water hose is filling up with water. You're pushing air out, you're putting water in. So there's more mass going in than there is coming out for a period of time. Now, that happens pretty quickly, especially if you've got a lot of volume coming out of your faucet. So it doesn't take long for this to reach 0, but there's a period of time where it is non-zero while this thing is filling up. And then once that water does start coming out of the end of the hose, again, the hose being my system, there's a period of time where the water coming out of that hose is really hot. If that hose has been sitting in the sun, that hose is really hot. So the water coming out of the hose initially is going to be really hot. In fact, it can actually burn your skin if you're not careful, if it's a hot enough day. So there's a period of time while the hose itself, the energy of the hose itself, will decrease. We've talked about the specific heats and the internal energy change. So this quantifies the internal energy change of the garden hose itself. There's a period of time where that temperature of that garden hose, which is directly proportional to the internal energy of the garden hose, is decreasing. It's cooling down as the water flows through it. So there's a period of time when the garden hose, the system, is losing energy as that water flows through it. Okay? So this is the unsteady point in the operation. Now after you reach a period of time where you've pushed water through this garden hose long enough that you'll get the same mass coming in as you go out, and you'll get a point in time where the garden hose is no longer cooling off. The garden hose is already cooled off. And so you'll have that the energy in is equal to the energy out. The garden hose itself is not changing energy. Now that doesn't mean you couldn't have heat in and mass coming in one end of the garden hose, and then coming out of the other end of the garden hose you have a higher temperature of the water, meaning the heat that goes in throughout the garden hose contributes to a temperature change in the water, but the garden hose itself, the system, that doesn't change. So that gets pretty in-depth there, but again, unsteady flow is this point in time where the system's either warming up or it's cooling down, or it's filling up with mass, or it's expending mass. So here's the thing. The examples of unsteady flow that we could point to, they don't typically operate in an unsteady fashion for an infinite amount of time. The garden hose example I gave you, you'll reach a point where you reach a steady flow point where the temperature of the garden hose, it remains constant, and you reach a point where the mass into the garden hose equals the mass out of the garden hose. So you do reach this steady flow point where the change is zero. You could have a balloon where we're filling up a balloon, or after you've filled the balloon up and you let it go, you reach this, it's only going to go when those are both unsteady situations where I'm filling the balloon up, or if I let it go and it just kind of shoots around the room. Those are both unsteady situations. So kind of the scenarios, what you have is two scenarios. If a system operates in an unsteady fashion too long, think about the balloon filling up. If I continue to fill that balloon up, it's going to explode, right? If I'm filling up a balloon and I continue to fill it up, I will reach the limit of that balloon and it will explode. That's one possibility. Or it will exhaust. So if I let that balloon go after I've put air into it, and now it's operating in an unsteady situation in the opposite direction, it'll hit a point where it's exhausted all of its potential energy, right? So those are those are the two scenarios you can encounter that are unsteady flow. Is eventually it's either going, three scenarios. It's either going to blow up, it's going to exhaust itself, or it will reach a steady flow condition like the garden hose, where if you run water through it and if you can maintain constant input conditions over a long enough period of time, it's feasible you'll reach a steady flow condition. But in the case of like a balloon filling up, we can't maintain that inlet condition. Eventually the balloon cannot sustain that increased pressure. Okay. Same thing if we're operating a turbine, or if we're operating a turbine off of a tank full of compressed gas. Eventually that tank of compressed gas is going to run out of air or gas, and it's no longer going to be able to spin the turbine. So this is only going to operate for a period of time. Again, these are examples of unsteady flow, but these are not normally what we will encounter. Normally we'll encounter the situation where we have steady flow. We want to maintain it so long as we can maintain the inlet conditions. But if we do consider unsteady flow, we have to understand both the first law of thermo and the conservation of mass become differential equations. And I'm not expecting you, as I've said multiple times, I'm not expecting you to have an in-depth understanding of differential equations. Excuse me, but that doesn't mean we can't have a basic understanding of them. Hopefully we talked maybe a little bit in the calculus class about differentials, and that's okay. If not, we'll do a little bit here. I'm not expecting to have an understanding of them. Even if you've had diffie, I don't expect you to have a lot of understanding of them. Here's what we're going to do. Kind of like we did with steady flow control volumes, we said, look, we can just assume this goes to 0. We're not going to assume it goes to 0, but there is another simplification we can employ. We can employ what we call uniform flow. Uniform flow means that we assume that the mass leaving or entering the system, the rate of mass entering or leaving the system is constant for a given amount of time, for a very short period of time. The change in energy is constant over a very short period of time. And the properties of that mass as it enters or leaves the system is constant for a short period of time. Another example I like to point to is the aerosol cans that we use to clean electronics. I wish I had one here and I could spray it for you and show you. That's an example. Any kind of aerosol can, right? Any kind of can that you would spray. That's an example of an unsteady flow situation. So you push that valve open, you get it to spray, and if you hold it open for a really long period of time, what happens? Alright, so again, can of aerosol, like the electronics cleaner, if I hold that can open for a long period of time, eventually that can gets cold, right? Because what's happening is the contents inside the can are expanding, right? They're growing, and as those contents expand into the vacated area that the mass is now left, the stuff that gets propelled out of the can is left, so the remaining mass expands into that area. And because it's expanding, it's doing work, so to speak, it's losing energy, it's going to a lower energy state, and so it gets cold. So what happens there, what we're saying here with uniform flow is we're not going to worry about a can or a system that's operating for a really long period of time. Think about that aerosol can if I just squeeze it and then let it go. Just a quick spray, and another quick spray, and another quick spray, over a very short period of time. The properties of the contents of the can are pretty constant. Right? Now again, you leave it open, leave that can open for a long period of time, and that's a different story. Those properties do change. But if we just talk about a very short period of time, spray, 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 not very long, these are reasonable assumptions. The rate of mass coming out, so again, if I hold that can open for a long period of time, eventually the mass will start to slow down. It won't move as fast. But for just a short period of time, it's going to come out pretty constant. The energy change is going to be pretty constant, and properties of that mass coming out are going to be pretty constant. So if we do that, instead of dealing with differentials, I don't have to worry about differential size slices of time. Let's worry about a quantifiably small slice of time, a delta t. So a very short delta t instead of a differential delta t. Let's worry about a small delta t. And that's going to be a small energy change instead of a differential size energy change. So let's approximate these dEdTs and dmdTs. Let's approximate those as deltas. And then I can just move this delta over to the other side of the equation. And then I just take my rates, multiply by the amount of time over which it occurs, and that gives me the energy change for the system, and the same thing with the mass of the system. Okay? So here's an example. I thought we could work through an example real quick of this. How am I on time? Oh, this is not a bad place at all to stop. So I'm going to stop here, and we'll see how far into this example we can get, how many videos that takes. Okay? All right, we'll be back in a second.